we just kind of have to figure, well, in order to write a Taylor polynomial, you need f at, it's centered at 2, so f at 2, you need f prime at 2, you need f double prime at 2. What is f at 2 from the graph? We don't know for sure because they didn't label the y-axis, but what could it be? Based on all of these answers. 2, right? All of them start with a 2, so f at 2 must have been 2. So it's reasonable that that y-coordinate at this point, at the vertex, that y-coordinate could be 2. Plus they all were 2. Okay, f prime. From the graph, what is f prime at 2? Oh, I'm looking at the wrong. I was looking at the vertex. Sorry, it's slightly here. So what's f prime at 2? 1. It would be reasonable to be positive or negative, or to be 1. Our only option when we look at the second term, the ones that are x to the first, are either a negative 1 or a positive 1. And at 2, the slope is clearly positive. So I know that that's positive. Okay, what about f double prime? What do we look for on the graph to find f double prime? Concavity. Is it concave up or concave down? Up. So I know that's positive. So I know f at 2, so it has to start with a 2. F prime has to be a positive number because it was centered at 2, it's x plus 2 to the first power over 1 factorial. And then it has to be a positive number, x plus 2, no, sorry, not a plus 2, right? I need the opposite. This needs to be a minus 2. And squared over 2 factorial. So I would expect something like this, but I don't know what the second derivative is. I just know that it's positive. So I just pay attention to the sign. So on E, it has to be E because we have 2, which again, that's the same on all of them. F prime was positive and F double prime was positive. It's the only one that has the correct signs. Okay. All right. Did you guys have a chance to look over your final? Do you want to look at the first half of the final now? Yes. Okay, so let's look at, for today, so we don't spend too much time, let's do the non-calculator, so the first section that you took. So I think you have to go into last try's class. Slow it up on my. Not showing me all of them. Oh, all courses. So you have to go to your BCB, so last try's course, and then I'm navigating to the one that was on the Thursday, I think. No, it would have been Wednesday, the non-calculator. But again, you have to go back to the other course. All right. Who had a chance to look over these? Riz, I'll give you. Yeah, no, yeah.
Can you do the one where it was the graph and the answer, like, it was that one of the answers was like 1 and 3, and it had to do with concavity?
Okay, let's find it. Let's do the non-calculator today.
I think it was.
I don't see that one. On this one. So let's do that one tomorrow. Yeah, so let's look at the no calculator one. I think that's the one I meant to get into. Yeah, the no calculator one. Yeah.
Did you do number 7?
Yeah. Oh shoot. And I guess they were scrambled. So you're number 7. If you want to do it, I'll show you my 7. I don't know if it's gonna be the same.
Oh,
What was your question?
It's the integral of 3x plus 1 over x squared minus 4x plus 3.
There we go. This one. Okay, so what stands out to me on this one is it looks like it's going to be a partial fraction. So I would do the a over b, or a over something plus b over something. Sorry, I find it again. There we go. Okay. So I'm going to factor the denominator. the denominator looks like it's going to factor as an x minus 3 and an x minus 1. So I could rewrite this fraction as a over the first factor and b over the second, or you could switch the factors. And then we multiply and get rid of all of these denominators. So 3x plus 1, the a has to multiply by the factor it does not have. The b has to multiply by the factor it does not have. And then we make choices for a and b. So what could we let x equal to get rid of the a? 1. If we let x equal 1, we plug 1 in on the left. And when we plug 1 in on the left, that's going to give us 4. So 4 equals 1 minus 3, so that'd be a negative 2b. So I get that b equals a negative 2. And then we can do the same thing to get rid of b. So let's let x equal 3. So the left side would be 10. And then we have 2a. So I get a equals 5. Then those two values, I'm just going to come back up. Okay, a is 5, b is negative 2, and then I'll integrate these two pieces. So this would be 5 natural log of the absolute value of x minus 3. Then the negative 2 comes out, natural log of x minus 1. That answer there, yep, it looks like that's D, and then the plus C at the end. Okay,
They're not.
yeah, everybody, so it makes it, I know, scrambling and makes it harder to communicate too.
Can we do the limit as x goes to 0 of e to the x minus 1 over x?
I remember seeing that one. I believe that one's going to be a L'Hopital's rule. So he's talking about the limit of the fraction that had the e to the x in it. This one here. Okay, so if we try direct substitution, if we plug in 0, we get e to the 0 minus 1 over 0, which is 0 over 0. So that's why we can do L'Hopital's rule. What's the derivative of the numerator?
E to the x.
Yep, what's the derivative of the denominator?
1.
1. And then you take the limit as x approaches 0. So you get e to the 0, which is 1.
Oh,
I expect that we'd have more questions. We feel okay? Yeah, Kaylee.
The limit of h versus 0.
Yes, I know which one you're talking about. Okay. So she's asking about the one that has the limit with the sign, and there's an h goes to 0. So when I think h goes to 0, it makes me think definition of a derivative. Oh. Okay, this one, is that right? Yeah. Okay. So once I see the h goes to 0, I know that I'm going to compare it to the limit as h goes to 0. The formula is supposed to be f of x plus h minus the function of x all over h. So I want to focus on what comes after the minus. So this sine of pi thirds, that's the function that I'm taking the derivative of. So this limit is the definition of the derivative of f of x. So f of x is the function. So I see that and I think, okay, well, the function is sine of x. Now, they didn't write x, they wrote pi thirds. So that's the value I'm going to evaluate the derivative at. So we have to take the derivative of sine. Well, what's the derivative of sine? Cosine. So because it is the definition of a derivative, then we're just evaluating the derivative at pi thirds. So we need cosine at pi thirds, and cosine at 60 is a half, or cosine at pi thirds is a half. So the answer is B. Yeah.
Can you do the one about the like cube?
Yeah, the sine cubed one. Is that it?
No, like the
Oh, the related rate question. That cube, yes. The volume one. So there was a related rate about the volume of a cube. This one. So it says the cube with length x centimeters, so that tells us the volume of a cube. The volume is increasing at a rate of 40 cubic centimeters per minute. So that's the dV dt. So that's the rate that the volume is changing. It said increasing, so it is positive 40. At the instant when x equals 2, what is the rate of change of x? So they're asking us to find dx dt. So all we're going to do is take the derivative of the volume equation. So the derivative of volume, that side just becomes dv dt. The derivative of x cubed would be 3x squared. We just have to remember to attach the dx dt. And then we can just plug stuff in. dv dt is 40, x is 2, and we can solve for dx dt. So it really is just 40, let's see, 3 times 4 is 12, so 40 divided by 12.
Oh,
Makes sense. Yeah, Parker.
I don't, the one where you're taking the derivative of the integral from 3 to x.
Okay.
Do you just plug in the x?
If you're taking a derivative of an integral, yep, you can just plug it in. You just plug in the upper bound.
Okay.
Was that this one here with the trig?
Yeah.
Okay.
That's what it is.
So yeah, exactly. So it just says, this is fundamental theorem of calculus, that if you're asked to take a derivative of an integral, the upper bound just replaces it. So the correct answer was D.
Wait,
Yeah.
maybe the one with the like the trapezoidal.
Yeah. Did it give us a table? I don't remember. Is that a table question? Okay. Was it this one? Yes. Okay. Yeah, this one was kind of tricky because, and this again goes to how AP can take something that we're really good at. We're really good at the trapezoidal rule, and then they ask it in a slightly confusing way. So they don't tell us K. They want us to find the value of K so that the trapezoidal approximation is equal to 52. So I'm just going to set up the trapezoidal approximation. I'm going to write this table so I can write on top of it. So I've got 0, 2, 4, 6, 4, K, 8, 12. So the first trapezoid has a width of 2. So it's like width times the average of the bases. So 4 and K are the two numbers I'm going to average together. And then I'm timesing by 2 because that's the width. Then I go to the next one. The next one has a width of 2, and I'm averaging K and 8 together. The next one still has a width of 2, and I'm averaging 8 and 12 together. They're telling us that this equals 52. So we just have a pretty ugly equation that we have to solve. So if we solve this, I'm going to go ahead and multiply those 2's, cancel those. So I've got 4 plus K. The next one, those 2's cancel again. So I've got K plus 8. Those cancel. 8 and 12 is 20. So it's just this equation that we have to solve. So let's see. I get 2K. That's 8 and 4 is 12 plus 32 equals 52 minus the 32. And then divide. So I get K equals 10. So it was just setting it up and then algebraically solving for it. Yeah.
Can you remind me why you times it by 2?
Yeah, so it's a trapezoid is, think of it as it's still base times height, but we have two height, or we have two bases, the two parallel sides. So the base is you really have to average the bases. So to find an average, you add the two parallel sides and divide by 2. And then the height is this distance between. So it's like this is the height, that's the width of the interval, and then the two parallel sides you average together. So this is like base 1, and this is base 2. Does that make sense? All right. Okay, so we can take more questions tomorrow. We'll look at the calculator. Let's go ahead and switch gears to your questions from yesterday's assignment. So 8.4, the ratio test. Number 5 was asked. Let's do 5 as a quick review of. First, they told us that we had to use ratio test, but anytime I see a factorial, I would think to use ratio test too. Ratio test, you start by replacing the n with n plus 1. Make sure you keep it in parentheses. This is a common mistake I see. So that's 2 times n plus 1 factorial over n plus 1 times 3 to the n plus 1. This parenthesis is important because you've got to distribute the 2. So that really becomes 2n plus 2 quantity factorial, and the denominator, not too confusing. The 3 raised to the n plus 1, I'm just going to rewrite as 3 to the n times 3 to the first. So there's the n plus 1 term. And then you divide it by the original term. But when you divide by a fraction, you flip and multiply. So it becomes n times 3 to the n over quantity 2n factorial. So let's deal with these factorial first. This one and this one. If we were to reduce it, remember 2n plus 2 factorial is equal to itself times the previous one. The one before it would be 2n plus 1 times the one before it, which would be 2n times the one before it, and so on. And if we have 2n factorial, well, that's going to be 2n times the one before it, and so on. So all of these cancel out. So when you reduce those two, you're going to be left with a 2n plus 2 and a 2n plus 1. So that's how we can kind of simplify those two. Okay. I'm not too worried about this n and the n plus 1. They do not cancel each other out because there is a plus 1. So when we take the limit, they'll go away. But I'm going to leave an n on top, and on the bottom I have the n plus 1. Then I can go to the next thing that I want to compare. I've got this 3 to the n and these down here. Well, the 3 to the n can cancel out with the 3 to the n, so I'm just left with a 3 in the denominator. Are we all right with that? Reducing. Now we take the limit as n goes to infinity of this. In fact, I'm just going to squeeze it in right in front. So I want to take the limit as n goes to infinity. The numerator is a degree 3 and the denominator is a degree 1. So it's top heavy. Anytime it's top heavy, it goes to infinity. Infinity is greater than 1, so therefore it diverges by ratio test. What would have been an easier test to prove divergence? Even easier than that? Nth term test. The numerator of the original one goes to infinity faster than the denominator. So if I didn't have to use ratio test, nth term test would have been a lot faster. Okay, then number 13. Number 13, this one we can use any test we want. I like to use comparison tests. This one seems set up perfect for comparison tests. If I have like a polynomial over a polynomial. Okay, so anytime I've got that, I want to reduce it and then compare it to that. So when I do this, I'm just kind of looking at the leading term. So I'm thinking, okay, 3n over n squared. What does that reduce to? 3 over n. And even more simple, I could ignore the 3 if I wanted to, so I could compare it to 1 over n. So I'm choosing to compare it to this because 3n over n squared is 3 over n, but the 3 really doesn't make a difference. So I'm just going to compare it to 1 over n. What do I know about 1 over n? It's harmonic. So as long as you call it harmonic, you can just say that it diverges. Okay, so it's harmonic, so therefore it diverges. Now I'm going to choose to do limit comparison. I do not want to do direct comparison because I don't know whether that goes that way or whether it goes the other way. I don't want to think about that. So I'm just going to do the limit of the ratio. So the limit as n goes to infinity. It doesn't matter which one you do first, but one of the, either the one you are trying to find or the one you know, divided by the other one. But if I divide by a fraction, I flip and multiply. And I take the limit of this. What is the degree of the numerator? N squared. So in fact, I could say that this is equal to, I'll write this out, but you could skip this step. The numerator, the leading term is 3n squared. The leading term in the denominator is n squared. So it is equal to the limit of that, but that equals 3. Limit comparison is if you end up with a finite number, then both series will converge or diverge. So they both behave the same way. Since we proved this one diverges, we can conclude this one diverges by limit comparison test. Okay, so that limit comparison test, I think, is usually pretty fast if it's a polynomial over a polynomial. Okay, the other question was 17. This is where we can use any test. Something about this indicates to me what test I should use. What do you guys think? What was that?
Ratio.
Ratio. Yeah. What tells you what kind of makes you think ratio?
Factorial.
Factorial. Anytime I see factorial, that unless I can do nth term test where the factorial is on top, but on the bottom I'm thinking ratio test. So I'm going to change n to n plus 1. If I change n to n plus 1, I'd have n plus 1 minus 2. I'm just going to go ahead and simplify and say that's n minus 1. So that's this term when I've replaced n to n plus 1. Then the next one would be a 3 to the n plus 1. The denominator quantity, make sure you keep it in parentheses, factorial. So there's the n plus 1 term. I divide it by the nth term, or flip and multiply. So I get to here. Okay, if I focus on reducing, I do not have to reduce this n-1 and the n-2. That's fine. They'll take care of each other when I deal with the limit. So I still have the n-1 on top, and I have the n-2 on top. I like to deal with like common things at a time. So I'm comparing those two. Then I have this 3 to the n plus 1. That's 3 to the n times 3 to the first. So the 3 to the n cancels out. So I'm left with the 3 on top. Let's look at the n factorial. What's n factorial divided by n plus 1 factorial? 1 over n plus 1. We'll be left with an n plus 1 in the denominator. So those we've dealt with. And I've already dealt with the n-2. Those two I figured out. So now I have it reduced. So I'm just going to take the limit as n goes to infinity of this. Well, the numerator is really just 3n. The denominator is an n squared. So I'm taking the limit of that reduced function. But what's that? What is it?
It'd be just going to 0.
Good. It's just going to 0 because it's bottom heavy. Anytime it's bottom heavy, it's going to be 0. 0 is less than 1, so it converges by ratio test. And we're going to do a lot more ratio tests today too, so you get more practice. Okay, 18. Which of the following series is or are equivalent to this? I don't remember looking at this one. Hold on. Okay. Oh, because it has a different starting. Oh, I think if we write them out. So if I did the first term, I don't know, I can think of different ways, but I'm just going to write out a couple of terms. If I plug in 1, what's the first term in this series? If n equals 1. The numerator would be 2 over 2, so 1. Let's plug in 2. We have, if we plug in 2, we'd have 4 over 3. If we plug in 3, we'd have 6 over 4. And I'll do one more. If I plug in, let's see, I've done 1, 2, 3, I'm at 4, so I'd have 8 over 5. Dot, dot, dot. Okay, what's the first term here? This one is starting at 0. If I plug in 0, what's the numerator? 2. And if I plug in 0 on the bottom, I get 2 again. So its first term is 1. Then I plug in 1. If I plug in 1, I have 2 times 2, so a 4 on top and a 3 on the bottom. So far this looks the same. I'll do one more term just to check. If I plug in, I did 0, 1, now I'm at 2. I'd have 3 times 2, so 6 over 4. So this one is the same. So when in doubt, just kind of go back to just plugging in numbers and see if they're the same. Okay, if we do this one, we start with 0. If we plug 0 in, what do we get out? What's the first term? 0. So that one clearly is not the same because the first term doesn't match. This one, if we plug in 2, did I mess up? Yeah, Nathan.
B, it's the same function. It's the same function. It just starts at 0. So wouldn't, if we added 0 to the same thing?
Oh, thank you. You're right. So if we then do 1, if we then plug in 1, we would get the same thing. So you're right, because it is 0 plus 1 plus 4/3.
Starting in the spot.
It would, yeah, it's only okay because the first term is 0. So the sum would be the same. So it does end up being the same. Thank you. If we do C and we plug in 2, 2 times 2 is 4, 4 over 3, but oh, and it has that 1 in front. You guys see that 1 in front? So it has the 1 just out separate, and the first term in this would have been 4/3. And then it matches the rest of it. So this is equivalent. So that one's the same. If you have a series the way that they've written it on D, it's like the summation symbol is kind of like an integral. You can distribute it through addition and subtraction. So you could think of this as the sum of 2 minus the sum of 2 over n plus 1. So that's equivalent. The sum of 2 is just 2. So really that 2 is just by itself minus the sum of 2 over n plus 1. So that's equivalent. So the first term in this series, we start with the 2 because it has the 2 right here. Then we plug in 1. If we plug in 1, we'd have a 2 over 3, so we have a minus 2/3. I feel pretty confident in saying that's not the same.
If you plug in a 1,
Sorry, say that again.
if you plug in 1 for n, and then just be 2 over 2.
Oh, thank you. 2 over 2. I don't know how I got a 3. 2 over 2. And that's 2 minus 1. So our first term is 1. So it's looking actually promising. So let's plug in 2. If we plug in 2, we'd have 2 over 3. So we're minusing a 2 over 3. So I don't see that being the 4/3. I'm thinking no. What do you guys think? Let me do a quick check.
Wouldn't it still be 2 minus 2/3?
The 2 in front we only use once, not every time because it's not being summed each time. Let's see, this is 18, but it is saying all are equivalent. So it's just doing each one individually. You're right, because the 2 is in there. Let's back up. Let's not overcomplicate it. Let's just plug in n into each one and write the first few terms. If we plug in 1, we'd have 2 over 2, 2 minus 2 over 2, the first term is 1. If we plug in 2, we'd have 2/3, 2 minus 2/3 is 4/3. So this one does match. We could do the same thing here, just plug in 3 and it would be equivalent. So in this case, all are equivalent. So it's just kind of time consuming to plug in n to write the terms of the sequence to make it match. Okay, on 19, I believe it was E. E asks you to use your answer from part D to determine if G has a local min, max, or neither at 0. I'm trying to remember so we don't have to do the whole question. We don't have time to do the whole question. So I'm gonna look at on A we wrote F G. I'm gonna write out what we got on the previous part. Okay, so use your answer from part D. So from part D, we were supposed to write a 4th degree Taylor polynomial for G of X. G of X is I'm gonna write it, they ended up simplifying. I mean, we could end up simplifying, but I'm writing it out like this so you can see the pattern. Oh, I guess then they did simplify. Okay, so here's our G of X function. To determine if it has a min, max, or neither, I'm going to rely on the second derivative test, which has 2 parts to it. We want to know if in order to be a min or max, the first derivative has to be 0. How do I know that the first derivative is equal to 0? I can do it a couple of ways. I could just find the first derivative, evaluated at, because it wanted it at 0. I know that the derivative evaluated at 0 is 0. The most obvious way is there is no x term, right? The x term, so the coefficient of the x term is 0. But also, if you took the derivative of this, the derivative would be 8x and then 4x cubed, but then you plug in 0 and it's 0. So it meets the first criteria. This means it might be a max or a min. If the first derivative is equal to 0, it could be one or the other. Then I analyze the second derivative. If I know if the second derivative is positive or negative, then I know it's concavity, which would tell me that that value is a max or a min. Is the second derivative positive or negative? Where do I look in this polynomial to find the second derivative? Our coefficient of the x squared term. If the coefficient of the x squared term is positive, I know that the second derivative is positive. I don't even have to take the time to figure out what it is, or you could actually take the second derivative. But if it's positive, it's concave up. So if it's concave up and you have the derivative equal to 0, then that point is a min. So we have a min at x equals 0. So this is a good question. They ask this a lot on the AP test where they're having you use the second derivative test to determine if it's a max or a min. So you have to analyze the first derivative and the second derivative. All right, let's go ahead and switch gears. I want to talk about interval of convergence. So I'm going to go to this. We only have 4 examples, but they require a little bit of work. We've talked about an interval of convergence when we've done ratio tests back at the beginning, or not ratio test, geometric series test. Let me do a quick, oh shoot, that was in the last unit. Where if it converged, if it was centered at 0 and the radius of convergence was 1, the interval of convergence would be like -1 to 1. If it's a geometric series, what made it easier is we know a geometric series always diverges if the radius is 1. We'll just start this example. But we're going to do the ratio test. So we're going to start with our ratio test. The difference is there's an x in there where the questions on our previous assignment did not have an x. So we're just going to set it up and then we're going to say the values of the x that make this converge. So ratio test, we replace n with n plus 1. So I'm going to say 2 to the n plus 1 times x to the n plus 1 over n plus 1. Okay, so again, we're doing the ratio test, so the n plus 1 term. We divide by the nth term, so we're going to multiply by the reciprocal of the original. Whoops. And we're going to reduce. So as we reduce, I know that this 2 to the n and the 2 to the n plus 1, that's just going to reduce to a 2. Similarly, this x to the n plus 1 and the x to the n, that's going to reduce to just an x. So this simplifies. The numerator has a 2x and n, and the denominator has an n plus 1. You guys agree to right there? I've simplified. Now, just like on our last section, we still have to take the limit as n goes to infinity. What do we get as n goes to infinity? 2x. Good. You guys see how that comes out to be 2x? So unlike the last one we would just get a number because there wasn't an x. But our rule is these are equal, so we get the coefficient, and the coefficient happens to be 2x. In order for this to converge, we're trying to find what values of x make this converge. Well, ratio test tells us if the ratio, and it is the absolute value, if the absolute value is less than 1, then it will converge. So we want 2x to be less than 1. If the absolute value is less than 1, then 2x is sandwiched in between -1 and +1. So again, this should seem a little familiar to what we did with the geometric series. Then we solve for x. So to solve for x, we're going to divide by 2. So if x is between -0.5 and +0.5. Now, we're not done. Should have taken up so much space, but are we okay to here? What makes ratio test more difficult than geometric series test is we have to check the endpoints. By checking the endpoints, right now, I do not have equal to bars on that. So if it was a geometric series, it always diverges at 1. Here, it might converge at -0.5 and it might converge at 0.5, so we have to check. So when we check, I'm going to check what happens when x equals -0.5. So that means I'm going to take -0.5 into the original function. Instead of writing x, I'm going to write -0.5, and I'm going to simplify and see if that series converges. So this would give me the sum of 2 to the n times -0.5 to the n over n. Okay, so I'm just replacing the x with that endpoint value. Now I have to prove convergence or divergence of this series. So to prove convergence or divergence of this series, I want to try to simplify it. I'm going to look ahead. Okay, so I'm going to focus on this piece right here. That I could say, I see the alternating piece. So I'm going to just pull out a -1 to the n. Okay, so the negative is just alternating. I still have the 2 to the n. That's this 2 to the n. But 1/2 is the same as 2 to the -n. Or even better, let me show you an easier way to do it. Okay, if two things are being raised to the power of n, I'm just going to bring that n out. So really these two together, I can think of as 2 times -0.5 to the n, because they're both being raised to the n. What's 2 times -0.5? -1. So this really is equivalent to -1 to the n over n. So I had to simplify that. We should recognize this series. What do you guys think? It's the same thing as, maybe you'll recognize, it's just an alternating harmonic. I could separate the alternating piece from the 1 over n. This is an alternating harmonic series. Alternating harmonic converges. Or you could have proved convergence using alternating series test. It alternates, the limit goes to 0, and it's non-increasing. So because we proved that it converges, I am allowed to come back up and put an equal to bar right there. So we checked -0.5. We did prove that it converges. So that means that -0.5 is included in that interval of convergence. Now we have to check the other side. So now the other endpoint is 1/2. So I'm going to check what happens when x equals +1/2. So I'm going to rewrite the series. So it's very similar. I've got the sum 2 to the n, but now it's 1/2 to the n over n. If we simplify this, I'm going to do the same idea. They're both being raised to the n. 2 times 1/2 is what? 1. So this time the series is not alternating. It's just 1 over n. 1 to the n is 1. What's 1 over n? What series is that? Harmonic. Does harmonic converge or diverge? Diverge. So that, because it diverges, I do not include an equal to bar. So I cannot add an equal to bar to the 1/2. So we had to check the endpoints to see if it converges or diverges of those. Okay, so it's a lot of practice of the same stuff that we've done. Okay, let's look at 2. I'm going to do the shortcut on 2. I could do ratio test, but I recognize that 2 is geometric. If you recognize that it's geometric, it's going to save you time. It's geometric because the numerator and the denominator are both raised to this n. So if we rewrite this, I can rewrite this as x plus 1 over 2 to the n. You guys agree that those are equivalent? This is now a geometric series. If you can rewrite it as one quantity to the n, you can identify the ratio without having to go through the ratio test. What is the ratio? Yeah, the x plus 1 divided by 2. Our rule is for a geometric series, the absolute value of the ratio has to be less than 1. We sandwich it in between. So x plus 1 over 2 is sandwiched in between -1 and 1. Same thing as before. I'm just going to try to get x by itself. So I'll times by 2. And then I'll minus 1. So if we minus 1, I'm going to get -3. So x is sandwiched in between -3 and +1. On a geometric series, if you recognize that it's a geometric series, you do not have to check endpoints because a geometric series diverges if the ratio is equal to 1. So we always know that those will never be equal to ours. So on a geometric series, it diverges when when the ratio equals 1. So we never have to check the endpoints. So that one was faster. Okay, let's try one more. If you have a factorial, there's no way it's geometric, so you have to do ratio test. Okay, so if we do ratio test tells us to replace n with n plus 1. This one that's our n plus 1 term, so we just divide by the nth term. So I'm going to divide by the nth term. If we reduce, let's focus on the factorial first. N plus 1 factorial divided by n factorial. What does that reduce to? N plus 1. So we have an n plus 1 on top. Okay, then we come over to this, the x to the n plus 1 over x to the n. That's going to reduce and just leave us with an x. So ratio test, you do n plus 1 divided by n. Then you take the limit as n goes to infinity. What do you get as n goes to infinity? Infinity, right? That would give us infinity, except for one particular value of x. What value of x would that not equal infinity? 0. So this is true except when x equals 0. When x equals 0, the limit would also equal 0. So therefore, this This would give us the ratio, that ratio equals 0 when x equals 0 and 0 is less than 1. So it will converge only when x equals 0. So there's not like an interval of convergence, there's a point of convergence. So we will call this a point of convergence. It only will converge for one specific value of x. Every other point, it would make it be infinity, which is bigger than 0, bigger than 1. Okay, let's try one last one. When we do ratio test, remember we do absolute value bars, so that alternating piece I get to just ignore when I write the n plus 1 term. So the n plus 1 term, I have x to the 2 times n plus 1. Those parentheses are important because I'm going to have to distribute. The denominator, same thing, 2 times n plus 1 quantity factorial. I'm going to simplify, that's 2n plus 2, so I've got x to the second times, or sorry, x to the 2n times x to the second. Is all right with that. The denominator, when I distribute, I have 2n plus 2 factorial. So there's my n plus 1 term. I have to divide by the nth term. So I'm going to multiply by the reciprocal of the original. So 2n over x to the 2n. What can we cancel out? Great, the x to the 2n goes. We have to think about how to reduce this factorial. If I were to write those out, what factors would we have left? Very good. On the top or bottom? Bottom. The top would just be left with the x squared. The bottom would have a 2n plus 2, and it would have a 2n plus 1. Okay, so we reduce. What do we have left to do? We're doing ratio test. Very good. So we throw that limit as n goes to infinity. What do we get as n goes to infinity? 0. Whatever you get out, you compare to 1. How does that compare to 1? Less than 1. For what values of x is that less than 1? All values of x, right? No matter what we plug in for x, that's always. This is true for all x. So therefore, our interval of convergence, x can be anything from negative infinity to infinity. So for every value, so the interval of convergence is any value of x you want, you're always going to get 0, and 0 is less than 1. So it converges for all x. Well, we can't plug in infinity, but like, yeah, if for any large value, the denominator is still going, because the ratio would go, it would end up giving us a number close to 0 or a value less than 1. Then the note at the bottom is just saying if it's a geometric series, it's going to be faster, but I kind of showed you that on number 2, that if you recognize that it's geometric, you do not have to check endpoint. So sorry, I know that that was like quick, but I think we'll be okay. So here's 8.5, your 8.5 assignment. You just have 1 through 17. Let's take, I want to mention one thing. They ask us for a radius of convergence. The difference between a radius of convergence and interval of convergence, a radius of convergence is easier. So like on number 1, when we do an interval of convergence, we have to check the endpoints. If I just was asked to find the radius, this interval, the radius of convergence is a half. When you state a radius of convergence, they don't make us check the endpoints. You just say it's going to converge for a half in each direction. An interval of convergence, you have to check the endpoints. Okay, so when we do number 1, let's just do 1 really quick. So they want us to find the radius of convergence. The process is the same, so we're going to start the same way by doing the ratio test, unless you recognize that it's geometric, but I don't see this one being geometric. So I have 2x to the n plus 1. If I replace n with n plus 1, the denominator is n plus 2. I multiply by the reciprocal, and then I take the limit as n goes to infinity. Well, I guess I should reduce first. The 2x to the n plus 1 and the 2x to the n, that reduces to just a 2x on top. So when I reduce this, I get to here. What is the limit of this as n goes to infinity? 2x. Are you guys all right with that? Remember, you have to throw absolute value bars around that. So this will converge if the absolute value of 2x is less than 1. I'm going to do basically the same thing. I'm going to say, well, 2x has to be sandwiched in between -1 and +1. Divide by 2, and I would get x is between -0.5 and +0.5. But because the question asked for the radius of convergence and not the interval of convergence, I just get to finish by saying the radius of convergence is equal to 1/2. I do not have to check endpoints. If it asks for the interval of convergence, you'd have to check each endpoint to decide. Not too bad. So you get 2 of those. Now, just one last thing. Which of these are geometric? Because if you recognize it's geometric, it's going to save you a bunch of time. So look at 3 through 14. 4. See how this one's geometric? If it's geometric, what that means is you do not have to check endpoints because it will always diverge. So you could just start by saying, well, the ratio is x over 3. The absolute value of the ratio has to be less than 1. Sandwich it in between, get x, and you're done. Okay. Do you recognize another one that's geometric? Which one?
8.
8 is geometric. I'm going to just put a little g by it. So when you get to that one, think about how if you can find the ratio without using the ratio test, it's going to save you time.
14.
Okay, so I heard 11. Do you guys think we could make 11? 11 looks geometric because everything's to the end. You'd have to tweak it a little bit to figure it out. Okay, which other one did I hear?
14.
14, unfortunately not. This part works, but you have this extra piece that's not raised to the end. 9, again, 9 isn't because of that n in front. That n in front throws it off. I don't think I see any others. Okay, but at least those couple will be faster if you do geometric series tests. All right, sorry I talked so long today. This is your last new section though. So tomorrow we get to start reviewing. There's like one little other topic tomorrow. Yeah.
On 1, how did you get 1/2 the radius of the variance?
I divided by 2, so I took the 2x and I sandwiched it in between -1 and +1.
So what if you got like, what if x was between like -3 and 1?
Okay, so x was between -3 and +1. I say, okay, well, the width of this interval is 4, so the radius is 2. The radius is the distance from the center to the end.
Oh, right.
Does that kind of make sense?
Yeah.
So did you guys catch this? This is, he had a question. If your interval of convergence was -3 to 1, that distance is 4. So the radius would be 2. So the radius is the distance from the center to the end. So. All right, have a good day, you guys.
For the following students, please come to the attendance office. Alexa Earl. Kristen Johnson, David Tucker, Rick Winter, Stephanie Bishop, Charlie Mallory Hess, Brody Fraser, Glenn Larson, Jenna Thank you.